You are paying 3 times over for every byte you keep, and you have probably never seen the bill broken out that way. Your storage line says one number. Your data is sitting on 3 separate machines in 3 separate racks, and 2 of those copies exist only to be ignored until something dies. It is rarely a decision anyone signs off on. You inherit it, you keep it, and it quietly triples the money you spend on the least glamorous part of your system. You have also felt the other side of it. A disk dies at 2 in the morning, your pager goes off, and the thing that saves you is that boring second copy. So you keep paying. The cheaper design sounds like the kind of thing that loses customer data and costs you your job, so you never seriously price it out. Fair enough. But have you ever actually priced it out? Here is the part that should annoy you. There is a way to get the same durability for roughly half the money. It has been running in production at enormous scale for more than a decade, and most teams your size still have not touched it. Not out of laziness. Out of a very reasonable fear that you would be trading a bill you understand for outages you do not. Give the thing a name so we can keep score. Call it Archivist, your cold storage service, 400 terabytes of documents your customers uploaded and will almost certainly never read again. Archivist costs you real money every month and earns you nothing. Park that question while we work through this, since it is the one your finance lead will ask you first. If 2 designs give you the same odds of losing a file, why are you paying twice as much for one of them? This is worth your attention for a reason bigger than storage. You are deciding what you will spend to survive a hardware death nobody can predict, and you answer that same question every time you size a cluster or wave through a default setting. Get the reasoning right on Archivist and you get it right in 6 other places where it costs you more. And notice which way your instinct pulls before we start. When you want something to be safer, what do? You make another copy. That reflex is so strong that most of us never ask whether copying is the only way to be safe, or even a particularly good one. It turns out it is neither, and the alternative has a worse name and better arithmetic. Replication is the design you already run. You keep whole copies. 3 machines, 3 identical files, and any one of them can answer a read on its own. The rule is arithmetic you can do in your head. To survive 2 deaths at once, hold 3 copies. Storage overhead is the term for what that costs you, and here it is 3 times your raw data. 200%, pure surcharge, forever. So what is the cheapest fix? Compress the copies, obviously. Squeeze each replica and pay less for all 3. But that is not the answer, and it is worth seeing why it is not. Compression shrinks each copy by the same factor, so you still pay the same 3 times multiple on whatever is left, and your genuinely incompressible data, which is most of what people upload, shrinks by nothing at all. Let us try again with the multiple itself as the target rather than the bytes. So why not simply keep 2 copies instead of 3? Because that is not the same product either. 2 copies survive 1 death. The second death you are worried about is the one that arrives during the repair window, while the survivor is busy copying itself onto a fresh machine and everybody is watching a progress bar. Is 3 a superstition, then? It is not. 3 is a bet about how long repair takes. Erasure coding is a different answer to the same question, and its name is far worse than its idea. Take 1 file and cut it into 6 equal data shards. Compute 3 more shards from those 6, which we call parity. Now you hold 9 shards, spread across 9 machines, and here is the property that matters. Any 6 of the 9 are enough to reconstruct the original file exactly. Not approximately. Exactly, byte for byte. Read that again, because it should not be true. You threw away 3 of the 9 pieces, chosen by whichever machines happened to catch fire, and the file comes back whole. No copy of it existed anywhere. That is a genuinely strange and rather beautiful thing to be able to buy from a cloud console for fractions of a cent, and it is worth being briefly astonished by it before we go back to talking about invoices. Do the arithmetic out loud, since the arithmetic is the whole pitch. 9 shards carrying 6 shards of real data means your overhead is 9 divided by 6, which is 1.5 times your raw bytes. Replication charges you 3 times for the same appetite. Both designs here survive 3 machines dying at once. Half the cost, identical failure tolerance. The honest answer to why that feels like a trick is that most of us assume redundancy means duplication, and duplication is only one way to be redundant. Push the numbers further and the gap gets wider in a way that surprises people. Widen the layout to 10 data shards and 4 parity shards and your overhead falls to 1.4 times raw, while your tolerance rises to 4 simultaneous deaths. To match that with copies you would need 5 of them, which is 5 times raw. So the wider you go, the more embarrassing the comparison gets. Where does that stop? At the point where reading a damaged file means talking to 10 machines instead of 6, which is a cost that does not appear on the storage line at all. Note, this is not a new idea. Richard Hamming published the codes that make it work in 1950, and Claude Shannon had proved 2 years earlier that a noisy channel has a hard capacity you can approach with clever enough coding. The family most storage systems actually use Reed-Solomon codes, arrived in 1960. Your cloud provider is selling you mathematics older than nearly every programming language you have ever typed in. So how does the reconstruction work? Here is the mechanism, and it is smaller than the vocabulary around it. Treat your 6 data shards as 6 unknowns. Each parity shard is one linear equation over those unknowns, computed in finite field arithmetic so that every result stays exactly 1 byte wide. Lose any 3 shards and you are left with 6 equations and 6 unknowns, which is a solvable system. That is the entire secret. Linear algebra you met at 18 and never expected to pay a monthly invoice for. It is a genuinely elegant piece of engineering, and the jargon around it is doing more work than the idea. Does that mean parity is somehow more precious than data? It does not, and this is the detail that finally made it click for me. In this scheme, no shard is special. A parity shard is not a backup of anything, and a data shard has no privileged status. You have 9 equally ordinary pieces and a rule that any 6 of them determine the other 3. Which 6 survive is nobody's business. That symmetry is why the placement rules are simple enough to trust. Spread the 9 across as many independent failure domains as you have, and stop worrying about which ones. Now watch what that elegance costs you, because this is where the two designs really diverge. A replicated read is one network hop to one machine holding the whole file. An erasure-coded read of a healthy file is nearly as cheap, since the 6 data shards are stored plainly and can be concatenated. But a read of a file that has lost a shard becomes 6 reads, a decode step, and a reassembly. Your tail latency stops being about one slow disk and starts being about the slowest of 6 machines. How bad is that in practice? Work it through, because the shape of it matters more than any single number. If a single disk answers in 10 milliseconds on a good day and 40 on a bad one, and one request in 20 lands on a bad day, then a replicated read is bad one time in 20. A 6-shard read is bad whenever any of the 6 is bad, which is closer to 1 time in 4. You did not make any disk slower. You just gave yourself 6 chances to be unlucky instead of 1, and your 99th percentile notices immediately. Then there is repair, and repair is the number that ends most of these conversations. When one replica dies, you copy one file from one healthy machine, and the repair process touches 2 machines. And when one shard dies? You must read 6 surviving shards to rebuild that single lost shard. So one machine loss generates roughly 6 times the network traffic it would under replication, and it generates the traffic precisely when your cluster is already unhappy and your operators are already awake. Case in point, Facebook published a warm storage system called F4 that holds photos and videos almost nobody opens anymore. It moved from 3.6 copies of every byte down to about 2.1, using a 10 of 14 Reed-Solomon layout spread across 4 racks so that a whole rack could vanish. At their scale, that is not a rounding error. That is a data center they never had to pay for. Do not take my word for any of this, and do not take a vendor's word either. Here is how you would find out for Archivist in one afternoon. Take 200 of your real files, encode them with a 6 of 9 layout using any open library, and measure 3 things: bytes on disk, wall clock seconds to reconstruct one deleted shard, and the network bytes that reconstruction moved. Then delete one machine's worth of shards and measure all 3 again. The numbers you get are unlikely to match the numbers in any blog post, including the ones in this episode, and that is exactly the point. Your hardware, your file sizes, your network. What would make you abandon the idea? Decide that before you run the test, not after, or you will simply argue with whatever comes back. A fair threshold is repair time. If rebuilding one machine's worth of shards takes longer than your tolerance for running one failure short, the arithmetic on the storage line does not save you. Write that number down first. A test you can only pass is not a test. There is a clean shape to where each design wins, and it follows straight from the arithmetic, because the shards that saved you money are the same shards you must read back. Replication buys cheap reads and cheap repair with expensive storage. Erasure coding buys cheap storage with expensive repair and a read path with more moving parts. So the deciding question is not which one is better. It is which resource you have the least of. Here is the caveat that matters more than any of the numbers. Erasure coding does not protect you from the failure that actually kills companies, which is you deleting the wrong thing confidently. 9 shards of a file you truncated is 9 shards of a truncated file, reconstructible with perfect fidelity into garbage. Neither design is a backup. Both are answers to hardware dying, and hardware dying is the failure you are already best at surviving. The second limit is object size, and it is a harder limit than people expect. Why would coding a tiny record be pointless? Cut a 4 kilobyte row into 6 shards and you are writing 6 fragments, each with its own metadata entry, its own request, its own round trip, and the overhead you just saved on bytes comes straight back as overhead on operations. Most production systems draw a line somewhere near 1 megabyte and do not code anything below it. Where that line sits depends on how expensive your metadata layer is, which is a question only your own cluster can answer. In practice, the systems you already know blend the two designs and nobody puts it on a slide. A cluster commonly keeps 3 full replicas of hot, freshly written data, then encodes it into a wider layout once it goes cold and stops being read. Hot data pays the replication tax for speed. Cold data pays the coding tax for cheapness. Hadoop's distributed file system added erasure coding for precisely this reason. Ceph exposes it as a pool type, and Azure and Backblaze both publish their layouts if you want to read somebody else's homework. The tiering policy, not the coding choice, is where the real engineering lives. Which raises the question nobody enjoys. What happens when cold data turns out to be warm? A regulator asks for 7 years of documents, or somebody ships a feature that reads old records, and the tier you optimized for cheapness starts serving traffic it was never sized for. Does your system notice and promote those files back to replicas, or does it quietly serve them at degraded latency until a customer complains? That policy is the part you will actually operate, and it is usually the part nobody has written down. And now an admission, because the folklore here is thick. Those durability numbers everybody quotes, the 11 nines you see on a marketing slide, are model outputs rather than measurements. They assume failures are independent, and correlated failures are the entire reason your data ever disappears. A bad firmware release, a rack losing power, one operator running the same wrong command on every node in turn. You cannot validate 11 nines. As far as anyone knows, nobody has ever measured it on anything. We compute the number and we hope, and it is worth noticing how much of your comfort rests on that. So, back to the question you parked. Why would you pay twice as much for the same odds? The answer is that you are not really buying odds, you are buying a repair path you can reason about at 2 in the morning while somebody senior stands behind you asking for a time estimate. That is a genuine trade-off, and it is a defensible one. It is just not free, and until you have measured it you have no idea whether you are paying $200,000 a year for that comfort or 20. So here is your call to make, and it is not mine. Go and find the storage line on your own bill, and work out what fraction of it is second and third copies of data nobody has read this year. If that fraction is small, this was a pleasant piece of mathematics and you should cheerfully ignore it. If it is large enough to fund one engineer, the interesting question is no longer whether coding works, since Hamming settled that before your grandparents had a television. Is your team better at absorbing a bigger bill, or a harder repair path at 2 in the morning? That is a judgment about your people, and only you can make it.